Let's get started with a real two-column proof. Okay, so proofs are set up. There's many different types of proofs that you can do. There's paragraph proofs, there's flowchart proofs, and then the most common is a two-column proof. And in a two-column proof, you set it up as I did with the mini proofs, but you have a statements column and a reasons column. Okay, the statements are numbered that in such a way that it matches the same number as the reason. So we look at this proof. We're given a certain piece of information and we're given a proof statement. You're usually also given the figure along with it. So the first thing you want to do is set up your first statement and first reason, which is your given information. So I've already set it up here. So we can see that our first statement is exactly the same as the given statement in the proof. AC is equal to AB plus AB, and the reason is that it's given. Okay, so now here comes the actual hard part, right? Where do we go from here? We're given one statement, AC is equal to AB plus AB. That doesn't really help me do anything, right? So you want to look at the figure. What do you know by looking at that figure? We can see that B is between A and C on that segment, right? So because of that between point, we can use our second statement to be our segment addition postulate, right? That we know because AB is between A and C, AB plus BC equals AC. And our reason is segment addition postulate. That's why we're allowed to say that, right? That's the reason, because we already know that. Okay? Now, where do we go from here? Well, always think about your proof statement. The proof statement right here is always going to be the last statement in your proof. It's the very last thing, because that is the goal. Okay? The goal is to work to get to this statement right here. So, thinking about the steps that we need to take to get there, okay? We need to get an equation that says that AB is equal to BC. Now, remember we're talking about lengths here, right? That's why there's no notation on top of those points. But if you look at this given statement and the one that we just wrote, they are both equaling AC. So we learned about a property that would allow us to, if we know that a figure or a value is equal to something else, we could substitute it in, right? So if AC is equal to AB plus AB and AC is also equal to AB plus BC, our third statement is going to be substitution that says that AB plus BC equals AB plus AB. Okay, we literally substituted this in for that right there. So now that's gone, and then we have this statement that's left. Okay, what do you notice here now? Anything that you can do to thinking about that proof statement, AB is equal to BC. What you want to notice is that you have AB plus BC equals AB plus AB. You have an overlap, right? They have a common value on each side, which is AB. So thinking back to our algebra proofs, we could actually subtract out that subtraction property of equality. We can subtract AB from each side, right? Just like that. I'm going to subtract AB from each side. So my step 4, if I subtract AB from each side, we get BC is equal to AB. And our reason is the subtraction property of equality. And I put subtraction property of equality. This is something that we do in the beginning of in chapter 2, and as we work through we might end up dropping it off, but the idea here is that we're property of equality. We're subtracting equal values from each side. Okay, so I subtracted AB from the left and I also subtracted it from the right. Subtraction property occurs a lot when we're dealing with segment addition and angle addition postulate and things like that. So our proof is complete. We ended up with the proof statement, right? our last statement of our proof is the same as the proof statement that we were asked to do. So you did it. All right, so let's look at another proof. Here now we're going to be using angles. So copy this in your notebooks and get ready, set it up with your 2 columns. All right, so here we have our proof already set up. Notice I have my statement and my given statement and my reason, okay? And if we look at the proof statement, we're trying to prove that the measure of angle EBA is equal to the measure of angle DBC. So EBA is right here, and DBC is right here. We are trying to prove that those 2 measures are equal. Okay, so let's see where we go from here. Knowing that the measure of angle 1 is equal to angle 3, okay, that's going to be helpful. May not be so straight up that you see it right now, but notice the markings that I have, right, from when I look at angle EBA and angle DBC. They're actually overlapping at an angle right here. What angle are they overlapping at? That would be angle 2, right? So there's a common, when you have a common angle or segment, or there's like an overlap between them, those common interior points, right? We use a property called the reflexive property, which basically just sets the angle or the segment equal to itself. So we know that the measure of angle 2 is equal to the measure of angle 2. So when we say this, we're going to use, well, as I said, when the angles are equal to themselves, that is going to become the reflexive property, which means it's equal to itself. Okay? Now we have to try to come up with a way that we could get angle EBA and angle DBC, and that's where this link of the reflexive property is going to help us. We know, right, that the measure of angle EBA, if I look at angle EBA, that is comprised of angle 2 and angle 3. So that's angle addition postulate. So we're going to say the measure of angle EBA is equal to the measure of angle 2 plus the measure of angle 3. Now, because of the same reason, which would be angle addition postulate. Alright, now because I'm going to have the same reason, I'm also going to look at angle DBC. Well, the measure of angle DBC is of the measure of angle 2 plus the measure of angle 1. And sorry, because this is the same reason, which is the angle addition postulate, I can leave it as the same number. Okay, this is something that we do in the middle of a proof. I don't usually like to do it at the end of a proof. If we're using a proof statement, I like to have the proof statement as its own number, but here in the middle of a proof, if we're doing 2 statements that involve the same reason, we could keep them just as one number. Now we can see here that we brought angle EBA and angle DBC into the proof. Now look at what those 2 angles are being equal to because of that angle addition postulate. We have the measure of angle 2 plus the measure of angle 3, and then here we have the measure of angle 2 plus the measure of angle 1. Now remember, right here we know that the measure of angle 1 is equal to the measure of angle 3. So you have actually 2 options, but same reason, which is substitution. We could substitute angle 1 in for angle 3 here, and if we did that, then these 2 angles are equal to the same sum, right? So that's actually what I'm going to do. Or the other way, you can actually, oops, sorry about that. You could actually substitute angle 3 in for angle 1. So you could go either way, right? There's more than one answer here. But I'm going to say now that the measure of angle EBA is equal to the measure of angle 2 plus the measure of angle 1. And our reason is substitution. I substituted angle 1 in for this angle 3, and that's what I came up with. Okay? Now, look here. These are the same sum, equaling 2 different angles. So, what do we have again? We have another substitution. But yes, we could technically write this as the same number because it's the same reason, but our result is going to be that the measure of angle EBA is equal to the measure of angle DBC. So that's our proof statement. So we're actually finished. So I always like to have my proof statement as my a separate number. Keep it separate from the rest of the proof. That stands out to us, right? So now we are finished. So this was a proof using angle addition postulate and substitution. We brought in that reflexive property because here we want to make sure that we know that every part of this sum is equal to the other. So we knew that 1 and 3 were equal to each other. We knew 2 is equal to 2. Sounds a little redundant, but it's very important, especially when we get to those more sophisticated proofs. Okay?